to the end of this section. But before we discuss the last example, I just want you to give a brief application of this line integral of a vector field. So maybe in physics you will learn about these types of line integrals, and using these line integrals we can calculate the work done by a force field on a particle. So basically, work done by a force field F on a particle traversing a path C is the line integral F dot ds. So just remember that using this line integral of a vector field, we can calculate the work. Okay, now here is the last example. Now in this example, we are going to calculate the line integral of a vector field along two different paths that connects the same initial point and the terminal point. So we are given a vector field F. Vector field is xy squared comma x squared y, and we want to evaluate this line integral between the points 0 comma 0 and 2 comma 4 along the following different paths. Path 1 is the line segment connecting the points. So if I draw a picture, for path 1, so this is the x-axis, this is the y-axis, this is your initial point, and terminal point is 2 comma 4. So now here this is 0 comma 0. Okay, so this is your path 1, let's say C1. And the second path is the parabolic arc y equals x squared connecting the same 2 points. So let's draw that second path. This is path 1. Here we have path 2. Path 2 is a parabolic arc. So be something like this. This is your C2. And the equation of this parabola is y equals x squared. And the equation of this straight line should be y equals to 2x. Because the slope of this line is 2, it goes to the origin. Therefore, the equation of the line should be y equals to 2x. Okay, let's calculate the line integral along the path C1. So line integral along C1, this is F dot ds equals to integral from a to b f on the curve C1 of t dot C1 prime t dt. But now we want the parametric representation of C1 and C2. Okay. So now we know how to get the parametric representation of a graph like this. So we take x equals to t, y equals to, since x equals to t, y equals to 2t. And similarly, for the second path, we take x equals to t, therefore y should be t squared. Now, what is the range of t? Here the range of t should be 0 to 2. Similarly, the range of t for the second path should be 0 to 2. and my vector field is this, so we need this one. And we need this one too. Okay, let's evaluate the first line integral. T goes from 0 to 2. We have a vector field f here. X equals to t. So this is your x coordinate. That's your y coordinate. X equals to t, y equals to 2t. So we have 2t squared, comma, t squared times 2t. This is the value of the vector field on the curve. Dot c1 prime. c1 prime should be 1 comma 2 dt. Let's integrate this. Actually, let's simplify the integrand. So if you take this dot product, you will get t times 2t squared plus 2 times t squared times 2t dt. If you simplify this, what do you get? You will get t times 4t squared plus 4t to the power 3 dt. Again, you have the integral that goes from 0 to 2. So basically your integrand can be simplified to 8t cubed dt. If you integrate this, you will get 8 times t to the power 4 over 4. Lower limit is 0 and the upper limit is 4. Now this, if you simplify 8 over 4, you should get 2. So this is 2. So you have 2 times, I think I made a mistake here, this should be 2. 2 times 2 to the power 4, which equals to 2 to the power 4 is 16. 16 times 2 is 32. Okay. Therefore, the line integral of the vector field f over the curve C1 equals to 32. Okay. Now we are going to consider the second path. Let me change this. This should be C2, should be C2, this should be C2. Now C2t equals to t comma t squared, and in this case t goes from 0 to 2. Okay, let's calculate the line integral. Zero to 2. Now we need to express the vector field in terms of t. This is your x coordinate and this is your y coordinate. So x is t, y is t squared. So we have the square of t squared, comma, t squared times t squared, dot c2 prime, that equals to 1 comma 2t dt. Okay, let's calculate this dot product. So basically you will get 1 times 1 times this first component. This is t to the power 4 times t is t to the power 5 plus 2 times, here we have 2t times this, so this is t to the power 4. T to the power 4 times 2t should be 2 times t to the power 5 dt. Our integrand simplified to 3 t to the power 5 dt. Okay, if you integrate this, you should get 3 t to the power 6 over 6. Lower limit is 0, upper limit is 2. So basically you will get 3 over 6 is 1/2 times 1/2 times 2 to the power 6 minus 0. This is 32. This means line integral of f, the vector field f over the curve C2 equals to 32 as well. Okay, now let's go back to the problem. So what we did was we calculate the line integral of a vector field along two different paths, but in these two paths we have the same initial and final points, and our calculation shows that the line integral over these two paths gives the same value, which equals to 32. Now in general this is not true. Actually it depends on the vector field. So in general, let's say this is not true. This is not true in general. It means sometimes for the same initial and terminal points, if you calculate the line integral along two different paths, sometimes you can get two different values. But in this case we got the same value. So but when this is true, it is true, the line integral is said to be path independent. So your line integral does not depend on the path. Actually this is the motivation for the next section, 13.3. Next section we will talk about this path independent and these types of vector fields. Thank you.